Professor Bialis here. In this video we're going to be talking about section 10.2, which covers rational exponents. Now remember, whenever you see that word rational, that simply means fractions. So you're going to have exponents that are fractions. So let's see first how to translate those, what do they mean, and then we're going to be working with those a little bit. So the first thing to do is lay out this notation. Because remember, an exponent tells you to multiply that base by itself that many times. How would I multiply a base by a fractional amount of times? What that really does is it creates another way of writing a radical. This right here means the same as the nth root of a to the m. Okay? So this is a rational exponent notation. This is radical notation. Notation is a way of writing it. These mean the same thing. Just like 3/4 means the same as 0.75. Different ways of writing it, different ways of writing it. Let's start off by translating back and forth a few of them. So let's say I have let's say x to the 1/2. That would simply mean square root of x to the first. Now really all I would write there is that, but I want you to see where everything is going. If I have x to the 2/5, that would be the 5th root of x squared. Now something I want you to be aware of is when you write it like this, you do have an alternative version and an alternative option to write it like this. Okay? So a lot of times we jump to this, but when you're calculating something with a numerical base, a lot of times this is going to be a lot easier to work with. We're going to see that in examples later on in this section. But I want you to realize that there is this option. If there's just an x like there is here, honestly I would leave it like this. Just kind of tidy it up and pull it all together. But if we're actually calculating and taking the root, this is a lot of times a lot easier to deal with. Okay, because that radicand stays a little smaller when you pull that square out. Okay? How about something like this? Let's say we have 27 to the 2/3. Let me show you that. So if we were to translate that, we would write the cube root of 27 squared. Now here's the problem with that. If you want to carry that out, you have to square 27, get a big number, and then find the cube root. Instead, write it like this. Cube root of 27 squared. That's a different story. Because now what's the cube root of 27? 3 squared, and you got a 9. That's what I meant by pull that out when you have to actually carry out the numerical process. This was fine here, not so nice there. So we can pull that out, whittle that down quite a bit, and then we have a nice, easy calculation in front of us. Okay? So let's translate the other way. Let's say we've got 4th root of x to the, let's say, 3rd. That would simply be x to the 3/4. Okay? Now one thing I want to show you, let's say we have this. Okay? No big deal. We can't really do anything with that, but if we write it as a rational exponent, what's 2/4? 2/4 is a 1/2. If we translated that back to a radical, that would just be a square root of x. So what this allows us to do sometimes is simplify radicals that otherwise we wouldn't be able to touch. Normally, what do? We take this divided by that. That's where this fraction idea is coming from. Okay? But if we can't carry that out nicely, 2 divided by 4 becomes a fraction, simplify the fraction, and now that radical becomes simplified as well. Okay? We're going to really dig into simplifying radicals in the next section, but just simplifying those exponents and indices can be very helpful when we're dealing with these problems. Okay, so the first portion of this is, again, just knowing this relationship here and translating from one to the other. Okay, when is it going to be better to do rational exponents versus radical notation? It depends. Sometimes I want to use exponent rules, so let's write it as an exponent. Other times I want to use radical rules, so let's write it as a radical. In this section, it's very important that you read the instructions, because the problems they throw at you will say, use radical notation to, blah, 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 to do whatever they want you to do to the problem. Or use rational exponents to carry out the problem. So they'll tell you what notation to look for. You just have to pay attention and be listening for it. Okay? So let's move on to something a little different. So let's say we have something like this. Now they say use properties of exponents. Now what properties are they really talking about? If you look back on a video that is section 5.1 and 5.5, I go through in detail all the properties of exponents that there are. What they're trying to get you to do here is use those same properties now on fractional exponents. There's nothing more to it. This is the same thing as what was covered back in chapter 5. It's just now there's fractions for exponents. So when we multiplied like bases, what did we do with those exponents? This is the same problem as me saying this. When we did this back in chapter 5, we added the exponents. What do we have to do over here? We have to add the exponents, but now we're adding fractions. So those same fraction addition rules have to be applied. So in order to add fractions, we need a common denominator. So common denominator between 3 and 4 is going to be a 12. I multiply 3 by a 4 to make it a 12, so 1 times 4 is 4. I multiply a 4 by 3 to make it a 12, so 1 times 3 is 3. And then I get 7 twelfths. That's it. Now, could we translate that now into a radical? You can, but they don't need you to do that in this case. They just want you to take this, simplify using those exponents, and then you're done. If you can, always simplify this fraction here. Because it's still a fraction, we can simplify it. Okay, let's look at a couple more. Now in this case, we've got the same base of 9, and then we've got these two exponents. What did we do with the exponents when we were dividing like bases? We subtracted them. Now, if you do look back in those chapter 5 videos, I would always say, who wins, who loses kind of thing, and I'll cross them off. That's not so nice in this case, okay? So in this case, I would just subtract them because the fractions kind of put another layer of complexity on there. So I subtract them. They already have the common denominator. So 2 minus 12 is negative 10 over 5. Simplify that to a negative 2, but never leave a negative exponent. So what we have is a fraction there, and we flip that fraction, so we've got 1 over 9 squared. 9 squared then is 81. And that's it. Now, again, I really spelled that out. If you want to, let's say, skip this step and go right to there, that's fine. Just be careful. Don't skip too many steps and then create a mistake for yourself. Okay? How how about this? Okay, this is a very clear distribution problem. So we're multiplying this by that and that. But remember, when we multiply those like bases, we add the exponents. So the first thing we have is x to the 3/4 times x to the 1/4 minus x to the 3/4 times x cubed. Okay, again, add the exponents. So what we have is x to the 4/4, or just x to the first, or just x, minus, and then here we add up. Now if you want to use mixed numbers as an intermediate step, 3/4 plus 3 is 3 3/4. Picture that in your head, and then multiply to get a 12, plus 3 is 15/4. Never use a rational exponent that's a mixed number. It always has to be improper. But if you want to, again, just in the meantime, write that down so you can picture it in your head a little easier, that's fine. Just make sure you convert it back to that 15/4. Okay? And that's pretty much it. That's all there is to it. Okay? Again, all you did here was add and add. That's really what it came down to. It's just, it was embedded in this rational exponent type of situation. Okay? Now, this last bunch of problems, it's going to be very important that you listen to the instructions. Okay, I'm going to write these out. It says, use rational exponents to simplify. Okay. The other thing they say a lot in these later sections is that you should always assume variables represent positive real numbers. If you look back in the section 1 discussion, that would tell you that you don't need to worry about absolute values. Okay. So this is just work with the variables, the exponents. Don't worry about any absolute value bars in these cases. Okay. They just try and keep it simple so we can focus on the task at hand. Okay. So let's start out with this. Okay. Now again, it says use rational exponents to simplify. What that tells you is they don't want you to work with this radical. If they start with a radical, they want you to end with a radical, but don't use it while you're going through the problem. So what that means is I need to translate that. Convert it into that other notation. Once you make that conversion, well now wait a minute. This is a fraction that I can very easily simplify. And once I simplify that fraction, the radical is now simplified. Because instead of a 10th root, I just have a regular square root. And then a y to the first. I'm just going to clean that up. And I've got that. Okay? So again, they tell you I need to use rational exponents to change this radical into this radical. Let's look at another one. Okay, now this one's a little tricky because if you just leave it as is, you get 9, there's a 1 there, so to the 1/4. There's not really anything to do with that. But the name of the game here is exponents. Think about a 9. Can I rewrite a 9 using an exponent? Again, if there's not something there to work with, try and get something in there that will help you along. That doesn't mean change the problem, but maybe write something in a different way. 4 quarters and a dollar bill are the same thing, but they work differently. Okay? So, or they have different possibilities, in terms of, putting a coin in a machine and whatnot. So if let's say we're here, 9, I want to think instead as a 3 squared. So all I did was take that 9, and now I wrote it as a 3 squared. But now what do I do with these exponents? The exponent rules tell us we multiply them. So I've got a 2/4 or a 1/2, which is a square root of 3. So a 4th root of 9 is the same as a square root of 3. And all that's based on is simplifying a fraction. Nothing more than that. Okay? Let's look at one more. Like this, and then we'll get into one more type of problem, and then that'll be it. Okay? We have to be careful with our organization in a problem like this. Same basic concept, but just be organized about it. So first I want rational exponents. That's going to convert to that. Because again, we can assume or kind of picture this to a first power. Okay? Now what we're going to then do is distribute that 1/9, apply it to everything inside. So we have an a to the 6/9 and then an n to the 3/9. Okay, now what are those fractions capable of? They're capable of reducing. Okay, as a radical, I can't do anything with that. There's no rule for radicals that allows me to manipulate this, but I can manipulate them when they're written as fractions. Okay, so I've got a to the 2/3, n to the 1/3. Now remember, if we start with a radical and we want to simplify the radical, we have to end as a radical. So we have to now back out of this problem, undo now the process going the other way. So before, I took this 1/9 and I put it onto each. So doesn't it stand to reason I can take those thirds and pull them out? So what I'm going to do is take those thirds out. So I have a squared n to the 1/3. And in essence, I'm factoring out that 1/3. But now how can I write that 1/3? If 1/9 was a 9th root, 1/3 should be a 3rd root or cube root. And there we go. Thing to remember, 1/2 square root, 1/3 cube root, 1/4 4th root, 1/5 5th root, and so on. Okay? And there we have it. Everything is now reduced. We still have the same components, but the exponents are less and the index is less. And that makes a big difference when it comes to calculation. Okay? Let's look at one more type of problem to finish this up. Use rational exponents to write as a single radical. So we're not simplifying a radical, we're bringing radicals together. So let's look at this. Okay, now when we look at radicals like this, in order to work with these, we need to have the same type of radical, the same index. Notice they're not, okay? So let's not work with them as radicals because we're kind of, we can't do anything with these. As a rational exponent, we have the exponent rules. We have fraction rules that we have at our disposal. So this square root of y, I'm going to think of as a y to the 1/2. Cube root of y is a y to the 1/3. Okay? And those ones can be thought to come from there. Now, in this case, we're not multiplying radicals. We're multiplying like bases where we would add the exponents. Now we have a different set of rules. Okay, so if we're adding those exponents, that can be done if we find common denominators. So what that is, we are looking for the same denominator of 6. A 2 times a 3 would make a 6, so we multiply by 3, and here we would multiply by 2. And then 3 over 6 plus 2 over 6 is 5 over 6. Once we get that, we can then convert back to a radical because they said to write it as a single radical. So once we convert that, it would be a 6th root of y to the 5th. And there we go. Okay? So again, sometimes written a certain way, we can't do anything with that. Okay? We have to change it so that it's something we can work with. Again, 4 quarters and $1. And if someone said, can I have a quarter? Okay, if you would just have a dollar bill, you can't help them. You can't break that apart. But as quarters, you can. Okay? So, let's now look at another one. So again, they have the same radicand, which is nice, but they have different indices, okay, the 3 and the 4. We can't work with that. So let's think of them instead as exponents. Because then, the fact that those bases now match allow us to do something. Whenever we divide like bases, we subtract the exponents. So we have x to the 1/3 minus 1/4. Okay? And now we're back to just subtracting those two fractions. So what we're left with is an x to the 4/12 minus 3/12, which would be 1/12. But remember, we need to convert that back to a radical. And if a cube root was 1/3, 4th root is 1/4, a 1/12 would simply be a 12th root of x. And there we go. Okay? Let's do one more. Now this is different because we have those numerical radicands. We don't just have variables that we're just going to kind of move around. We may have a little bit more calculation to do. Let's take this a step at a time though. We still want to have a single radical. So we can't do that because we have a square root, cube root, different types of radicals. So what I'm going to do is I'm going to convert them to rational exponents. Okay? Now, if we want those two to come together, what we're going to be aiming at are those denominators, because those denominators show us the indices. If the denominators match, that means the indices match, that means we can pull it together. Okay? These are not like bases where we just add the exponents together. But we now can manipulate these fractions because they're fractions. We can use fraction rules. So what I'm going to do is I am going to convert both of these to have a denominator of 6. So I have a 5 to the 3/6 times 2 to the 2/6. Multiply top and bottom by 3 here, top and bottom by 2 here. Okay? Now, what does that do for us? Again, I'm not trying to get the bases together necessarily. I'm trying to get one big radical. These bases, these denominators match, therefore I can pull them out. So what I'm going to do is I'm going to essentially factor out those sixths. So I have a 5 cubed times 2 squared to the 1/6. Now if you want to double check that, don't be afraid to redistribute that sixth. 1/6 times 3, that's 3 over 6. 1/6 times 2, that's 2 over 6. Okay? Now, remember, if I had a 1/2, it was a square root. 1/3 cube root. 1/6. I have a 6th root of 5 cubed times 2 squared. That's a single radical. Now technically, you did what they asked. You could be done, but it's always good to spell that out a little bit more. What is 5 cubed? 5 times 5 is 25. 25 times 25 is what? If you can't do that in your head, I'm sorry, 25 times 5, I'm sorry. If you can't do that in your head, do this. Again, 5 times 5 is 25 times another 5. I misspoke with a 25. So 5 times 5 is 25 times another 5. 5 times 2 is 10. 10 plus 2 is 12. That's a 125. So we've got the 6th root of 125 times 2 squared is 4. 125, if you want to multiply that by 4. 0, carry the 2. We've got 4 times 2 is 8, plus 2 is 10. Okay, carry the 1. 4 plus 1 is 5. So we've got a 6th root of 500. Still big numbers, but a lot simpler than this complicated looking thing right here. Okay, again, I apologize for misspeaking, but 5 cubed, 5 times 5 is 25, times another 5 gives you the 125. 125 times 4 gives you the 500. Okay, so it's all about indices and denominators. As an index, we can't touch those. They don't match and we're stuck. But here, as a denominator, we can make a match. We have a different set of rules we can play by. Okay, so that's what's really good about being able to write a radical notation versus a rational exponent. Okay, so just take your time with this. Remember, if you do want to review your exponent rules, I have a video on sections 5.1 and 5.5. It's a combo section video. Look at that. It'll explain all those basic rules, and we can apply them to these rational exponents. Okay, as always, keep working hard. Let me know if you have any questions, and I'll see you next time.